Tutorial 3, Question 3. A feed contains 20 mol% of CH4, 60 mol% of oxygen, and 20 mol% of CO2, carbon dioxide. The CH4 and O2 react to produce CO2, CO, and H2O. 95% conversion of methane is achieved, and the yield selectivity of CO2 from CH4 combustion to CO is 9.5. Determine the composition of the product gas for the system using A. Element balance and B. Species balance. So over here we draw up the process. So it's similar to question 2 in tutorial 3, which is the previous question. So your feed here, we shall give it a basis of 1 mole. So the feed contains 20% of CH4. This is in fraction. So that's 0.2 CH4, 0.6 O2, and 0.2 CO2. And you also cannot assume that everything is reacted. There may be some CH4 that is not being fully reacted, or O2 that is not completely reacted, so we need to have these two components still in the product stream. Then we know that there is CO2, okay, there's also CO and H2O that is produced. Okay. So part A, we will do element balance. We are given specification number 1, which is 95% conversion of methane. So the overall methane, only up to 95% of it is being converted. Meaning to say you will have remaining of 5% of methane left. That methane will come out in the product stream, and that can be calculated by taking 1 minus the conversion factor multiplied by the amount of, this one is the amount of methane coming in. So, and that is actually 0.2 moles, 0.2 times F, which is the feed, 1 mole. And you will find that the number of mole of CH4 coming out is 0.1 mole. Specification number 2 says that the selectivity of CO2 to CO is 9.5. That means that the fraction here, number of moles of CO2 out over the number of moles of CO coming out, is 9.5. And we can easily calculate the number of CO2 coming out with this, bringing this over. But we do not have the number of moles of CO coming out yet, right? So then we can do element balance using C. In this case, we have another element, which is O. In question 2, we do not have O, but we only have element C and element H. But in this question here, we have the element O. So we'll start with element C. So C is found in the feed, in CH4, the number of moles of CH4 going in. So same again. In 1 mole of CH4, there is only 1 C. So you multiply by 1 mole of C over 1 mole of CH4. In equals to out. Okay, very simple. So whatever comes out, you have CH4, the number of moles of CH4 coming out. C, only 1, so 1 over here. And you also have CO2 coming out. You only have 1 C here, so 1. And number of CO coming out, so that's 1 carbon. Simplify and put in the values. You have, this is 0.2 times the feet F, which is 0.2 times 1, equals to, this one was found over here, 0.01, okay, plus, so notice that this part here is number of CO2 coming out, so this is equal to 9.5 multiplied by the number of mole of CO coming out. So we replace this with this, okay, plus the number of moles coming out over here. This one is over here. So this one we are replacing this with this. And the final calculation gives us that the number of CO coming out is 0.037 mole. Then again, we can use this equation to calculate the number of CO2 coming out, which is 0.35 mole. Next, we will do the H element balance, which is the hydrogen. So hydrogen is found in CH4 in the feed, and H, you see there's 4H per mole of CH4, so times 4. And what else coming out has a H, H2O and CH4 only. There's only 2 components, so the number of CH4 coming out multiplied by 4 moles of H, and the number of H2O coming out multiplied by 2 moles of H. There's 2H here. Simplify it and you can get the number of H2O coming out is 0.38 moles. Next, we have the O element balance. So the total amount of things that we have found is this 0.38. Always double check what else that you need to find. What are the other unknowns that you need to find? CO2 out is 0.35. CO out is 0.037. CH4 out is 0.01. So we are left with this. Therefore, we need to do O element balance. So O is found, the element O is found in oxygen here and CO2 in the feed. So you have here the number of moles of oxygen in the feed. So you have 2O, so that's 2 moles of O per mole of O2, plus number of moles of carbon dioxide going in, and you have also 2 moles of O, okay, is equal to the output, which is the number of moles of CO2 coming out multiplied by 2 moles of O, plus the number of moles of CO coming out multiplied by 1. You only have 1 O here. And finally, number of moles of oxygen coming out, this is what you want to find, multiplied by 2. Substituting the values that we have found previously, and you can obtain the number of moles of O2 coming out is 0.24 moles. For part B, species balance, we will now have to look at the reaction equation. So we have 2 reactions. One is a complete combustion, one is a incomplete combustion. So the complete combustion produces CO2 while the incomplete combustion produces CO. So specification number 1, 95% of conversion of ethane. That means 0.95 is multiplied by the number of moles of CH4 going in, and that gives us 0.19. Again, this is the overall conversion for methane, which means the overall for these two reactions. Therefore, this 0.19 here, is actually a sum of the extent of reaction number 1 and extent of reaction number 2. Next, specification number 2, we have the selectivity of CO2 to CO is 9.5. That means the number of moles of CO2 coming out over the number of moles of CO coming out is equals to 9.5. So the number of moles of C2 coming out is actually equals to, because in our question we know that we have CO2 contained in the feed as well. Therefore, what comes out is actually the result of what goes in plus the number of moles of CO2 that is produced during the reaction. In reaction number 1 here, we have CO2 being produced. So the total amount of CO2 coming out is actually the sum of what goes in and the total amount of the CO2 that is being produced during the reaction. So number of moles of CO2 coming out is here. And we can further simplify it here. So the number of CO2 going in is 0.2 plus, since CO2 is our main product, okay, CO2 is our main product, therefore it is also the number of moles of CO2 formed during the reaction is actually during the reaction is actually the extent of reaction for reaction number 1. And for reaction number 2, the main product is carbon monoxide. So the number of CO formed comes out is actually the extent of reaction number 2. With that, we get this equation. Simplify it and we get this equation, because this is equals to 9.5. Solve using this equation and this equation. Use these two equations, solve them simultaneously to obtain the extent of reaction 1 and the extent of reaction 2. Then we can use this formula again, which was discussed in question 2. And for the number of moles of CH4 coming out is actually the number of moles of CH4 going in plus the extent of reaction number 1 and multiply by the stoichiometric number number 1 for CH4 and the extent of reaction number 2 multiplied by the stoichiometric number for reaction number 2 for CH4. So this one is 0.5. Please refer back to the question and your calculation and substitute all the values in. You should get 0.01 mole. Let's look at an example where the compound is not in another reaction. For example, the number of moles of CO2 coming out is equal to the number of mole of CO2 going in plus same formula. So this one is 0.2. We were given the percentage, the number of mole percent, and this one extent of reaction number 1. So CO2 is involved, is being produced in reaction 1. Okay, so the stoichiometric number here is 1, positive 1. So you will use extent of reaction 1, like so. But notice that this stoichiometric number for reaction 2 is 0. Why? That is because you do not see any CO2. You do not see any CO2 in reaction number 2. And when you do not see any reaction, you do not see the compound or the component in any particular reaction, you set the stoichiometric number to 0. That means this is gone. And you will solve for the number of CO2 coming out is 0.353. So do the same with the following to solve for number of moles of C2 coming out, number of moles of H2O coming out, as well as the number of moles of O2 coming out.